This section is on differentials, which involves using linear approximations to approximate functions. And a lot of what's going on is really tied up in this particular picture, this figure here. We have a function f, and we put a tangent line at c, and we go from c over to c plus delta x. That's a distance of delta x, which we're also going to say is equal to dx. And as we go over from c to c plus delta x, along the curve we go from a height of f of c to a height of f of c plus delta x. And so our change in y along the curve, the change in y along the curve is called delta y. That's the exact change. So delta y is the difference in the y values, f of c plus delta x minus f of c. Now, as far as a linear approximation, another way to look at this is we look at the red tangent line. So that's a linear, it's a line, tangent line. And now as we go over delta x equal to dx, we go up to this height here, and so we say this distance is dy. So delta y is the exact distance along the curve. Dy is the vertical distance if you go along the tangent line. And so here's your delta y definition. Again, if you want to find dy, we can do it by finding the derivative f prime of x, dy dx, different notation for the same thing. If you multiply dx to the other side, you get dy is f prime times dx. So basically, the rise is equal to the slope times the run. The slope is rise over run. So now we have the rise along the line is equal to our slope, which we get from a derivative, times the run. So now as far as looking at the error in this approximation, because the error is right here, that's the difference between the exact vertical distance you've changed, which is delta y, and the approximate dy. To look at the error, we can come over here. We see at this point here, we're making the approximation, it's concave down. If we go very close to the point, then our error is very small. As we get farther away, of course, our error is going to get bigger. Also, we are currently over-approximating. That is, the tangent line's above the curve. We're over-approximating because the curve is concave down, so tangent lines are above. Now, a little bit. So now at the point in question, well, we're still concave down there. If we try to change it around so that we make it concave up, we go over to perhaps to here. That's concave up now. Now we're under approximating because the line is below the curve for concave up. Okay, back over to some examples of different ways you can apply this. All right, if we're just given a function f of x equals rad x at x equals 4 and dx equals 0.2, and we want to find out what dy and delta y are. Well, first, if we want to find dy, f prime of x is dy dx, and so dy is equal to f prime of x dx. Okay. All right. Therefore, if you take a derivative of this, you get dy is half x to the negative a half dx. Plugging in 4, plugging in 0.2, you get dy is 0.05. So as you moved over 0.2, you moved up approximately 0.05 on the curve. This is approximate because this is a linear approximation using the tangent line. Now your delta y is the exact change in vertical distance along the curve. So you do f of 4.2 because you went from you ended at 4.2 minus f of 4 because you started at 4. So you do the ending height minus the initial height. So you plug in 4.2 and 4, you get 0.049, which is a little less. Now if we go ahead and just do a very rough sketch of rad x, looks like this, and you can see it's concave down, and so a tangent line is going to be above the curve. And so that's why dy being bigger than delta y makes sense. Okay, here's another example. We have y is equal to 1 minus 2x squared, x is 0, and our delta x dx is negative 0.1. Those are the same, delta x dx. It's delta y and dy, which would be different. Now if you draw it, you see we're at the vertex of a parabola, and so we expect dy to be anything because the tangent line is flat. And so here's dy is negative 4x dx. You plug in x is 0, plug in dx is negative 0.1, and you get 0. Now if you do delta y, now that's going to be the exact change in y. We started at 0, and we went negative 0.1, so that means our final x value is negative 0.1. So it's 1 minus 2, negative 0.1 squared, minus, because you subtract your y values, 1 minus 2 times 0 squared, and you simplify it, and you get negative 0.02. Okay. A couple other concepts that I want to point out. This is looking at example 3 in the textbook, and it has to do with propagated air on a sphere. You have a spherical ball of some sort, and it's got a radius of 0.7, but you could be off by as much as 0.1, and you want to find the propagated error of volume. So you differentiate, and you get dV is 4 pi r squared dr. You plug in, and this gives you the propagated error in volume. Again, it's approximate. If you want to get the exact difference, what you would do is do 4/3 pi, and then the biggest possible radius cubed minus 4/3 pi, the smallest possible radius cubed, to give you your delta V. Now, we also have the concept of relative error, percent error. You know, is this amount of error a big amount or not? Well, it depends upon what we're talking about. And being an inch off in the radius of the moon is not very much, but being an inch off in the radius of a billiard ball is a lot. So the way to get relative error is you do dV over V, and you can actually do a lot of cancellations prior to even plugging anything in. You get 3 dr over r, and plugging in these values, it's a 4.29% error for this particular example. Okay, here we have, this is dealing with the cube. So what we're looking at is we've got a side length of a cube is 12. You could be off by as much as 0.3. We want to find the propagated error in the volume, propagated error in surface area. So V is s cubed. So therefore dV is 3s squared ds. So we get 3 times 12 squared times 0.03, and that would be in inches cubed because it's a change in volume. Propagated error in area, differentiate and plug in again, and whatever that is, that's in inches squared. Here we have percent error for area. You could do whatever you got here, which is your dA divided by 6 times 12 squared, but you can also do a lot of cancellations before even plugging anything in. You take dA, 12s ds, divided by a, 6s squared, cancels to 2 ds over s, and then you could just plug in the 0.03 and the 12 and get your get your relative error, which can become a percent error if you just multiply it by 100. Okay, another thing we can do with differentials is approximating function values. And so if we want to approximate radical 17 using differentials, which is about 4.123, we can imagine we have this function y equals rad x, where x is 16. We choose 16 because it's close to 17 and it's something we can find the square root of. And therefore, to go from 16 to 17, we've got to make dx equal to 1. So what we do is we say dy is a half x to the negative a half dx. We differentiate. We plug in our x and our dx values, and we get 1/8. So basically, as we went over 1, we went up approximately 1/8. So rad 17 then is approximately rad 16, because that's the height we started at, plus our change in height. And so we end up with 4 1/8, 4.125. So I'm only off by thousandths. Now, if I were to choose something farther away from 17, like say 25, because you can take the square root of 25, then to get, so instead of choosing 16, I choose 25. Dx would have to be -8 to get down to the 17. And so you do the same sort of differential, you plug in the numbers, and you get -4/5. So now rad 17 is approximately rad 25 plus -4/5, which is now 4.2, which, as you'd expect, is not as good an approximation as if we choose a number closer to our original value. Now for cube root of 66, our function's y is equal to x to the 1/3, and x is 64, and therefore our dx is going to be 2. So therefore we've got dy is 1/3 x to the negative 2/3 dx. So to find a differential, you simply differentiate, multiply the dx to the other side. You plug in those values here, and you end up getting 1/24. So then cube root of 66 is approximately cube root of 64 plus that change in y, so 1/24. So 4 1/24, which if you want to then get the calculator out to compare, these are really quite close. They're the same through 3 decimal places. So one more thing, to find these differentials, basically all you've got to do then is take a derivative, separate the variables. So a quick example, y is equal to cosine x plus x. So dy is negative sine x plus 1, multiply the dx to the other side.